Hi, everyone. I will quickly present my work related to the modeling of natural catastrophes in this actual conference. But first, let me perhaps introduce myself. So my name is Arthur Charpentier. I'm currently professor at Université du Québec à Montréal in Canada, after being a professor in Rennes, in Brittany, in France, and in several schools in Paris area. Since 1 year, I'm involved in a joint research initiative on the theme unusual data for insurance that I will talk a little bit at the end of this talk. I might have met some of you during some internal training I did like 5 years ago on machine learning for actuaries. I can mention that I've been publishing a couple of books on actuarial and models and predictive modeling, including machine learning and statistical techniques. But I've been also working on inequalities and fairness more recently. And today we'll talk more about this climate modeling topic of mine. So here are a series of papers published over the past years. There were most of them were on the dynamics of natural catastrophes, on climate change and disaster. So I'm going to show you the logic of those publications. So in red, you get the old papers. Here you have the most recent two I'm going to talk about today, more specifically. I will end by a discussion on the very last two on the bottom right. But I'm going first to discuss a little bit this those red papers where I will present early work I've been doing on climate risk. So to come back on all papers, I can mention that I started working on those papers a long time ago, and it was about the dynamic of events, right? So it was on wind and islands. It was more on windstorms. There was a paper on heat wave, a paper on earthquake, another one on flood event, and most of them were with the same kind of pattern. The idea was to understand the dynamic and the temporal occurrence of natural catastrophes. I can mention that the starting point was an observation that was born from discussions I had with actuaries, and more specifically within the AXA NSA share on catastrophe risks around 2005, 2010. To make the long story short, when we were discussing, so I understood that there were a lot of catastrophe models that were sold that you can find in the industry. I think about RMS, Equiquat, and these kind of models. So it's very easy with this kind of model to generate events, possibly like a hurricane. So this is a trajectory of hurricanes. So in red, you can get past hurricanes that happen in the Atlantic Ocean. And it was possible to model this kind of dynamic or spatial dynamic of such a process. Here it's a very simple one where I have a Markovian model. So I assume that it's going to start somewhere, right? So I'm going to start somewhere and then I'm going to move around. And the idea was if I'm at some point, so I consider some grid here. And if I'm at some point, so let me perhaps try to make an example just to illustrate what I'm saying. So we have a grid. So assume that you are at some point here. Then I take all the past catastrophes or past hurricane that went through this small square in the grid. And I will consider all the trajectories. So where did they go afterwards? Once they occur here, where will they be within the next 6 hours? Right. So some of them will remain in this square, but some of them will move to the west, or they will move to the north. Right. So we can get the different locations of all the past hurricanes who went through this area and go and look at where they went afterwards. Right. So it's possible to generate some scenarios where we have all those points. So in red, for instance, you get all the points when I was drawing some simulation. So it's possible to get a spatial model for almost all events. And the main question was more on the frequency, because if I can get one big hurricanes, I still don't know how many hurricanes we expect to have, right? So we can get some Poisson model, but having a Poisson distribution for frequency is something extremely restrictive, because the Poisson process is related to this idea of having time between the events which are independent. And it was actually the question I was asking a few years ago, which was, can we clearly assume that we have independence between the different events? And the answer is most of the time no, right? So just to illustrate some past work I've been working on. So the first one that I can mention is the one on top, which is those series of 3 graphs. So it was earthquakes in the area of Japan, right? So we got Japan here, and we got a lot of past events. And the question was, if we have a hurricane, when will be the next one? If we have a big one, are we going to wait a long time before the next one, or will it be very, very quick? And there's this seismic gap hypothesis assumption that you can find in geophysics, saying that actually an earthquake is a release of energy, right? So if you have a big earthquake, it's very likely that you're going to have to wait a long time before getting another big one. It's very likely that you will have some small aftershocks, but the probability to get also in the same area another big one is usually extremely small. So we've been running some scenarios to see exactly which kind of dependence we got between the magnitude of the previous earthquake and the duration we have to wait before the next one. So it was some sort of model on the dynamics of earthquakes. The one you have on the bottom left is related to flood events. So it's the dynamic of flood events. And this one was based on some, so this is a river we have in Canada, right? So you see the level of the river, right? So we can see that it can be actually very low, but sometimes it can become extremely large. So in that case, when we exceed some thresholds, we can call that a flood event. And here we have some very precise data. It was on a daily basis, but we can get even more precise data. And we were using some sort of model that you can find in financial econometrics by that time. So it was introduced by Engel. It was the idea of autocorrelated duration models. So we're going to look at the duration between 2 events, the events being the 2 shocks we have. So here we have some excess of some threshold. And we were looking at a lot of things, which mainly the length we have to wait, but also the size of the flood, because we can have the area that you can observe here. And this area is more or less, so it's not the magnitude, but let's call that the magnitude of the flood event. It's how much water went above the threshold. So this is something that we were looking at. And the idea was more or less to confirm or to connect 2 papers extremely popular in hydrology. The first one being the work by Hurst. Hurst was working on the Nile. And what he observed is that when you look at the level of rivers, there is some extremely strong dependence. These were introduced the idea of long memory processes. So having long memory means you have a very strong autocorrelation with the past. And strangely, it's going to contradict what Émile Gumbel was saying about flood events. Émile Gumbel was working in France, especially in Lyon, and he was looking at the level of some rivers in Lyon. If I remember well, it should be the Rhône and the Saône. And what he did observe was that actually the maximum you can observe on rivers each year is independent from one year to the next one. So from his perspective, there was independence between flood events when you look at a specified point. And this is by assuming that we have this independence, that it actually introduced something which is extremely important in reinsurance and actual literature, with this idea of return period, right? So the idea of return period, which is to express a probability as a duration, actually comes from this idea of having events that are independent in time. But it's somewhere in between, because independence is extremely strong. Hurst approach say that actually we should have some strong correlation. So it should be somewhere in between, and this is what we can get when we have some high frequency data. And this is what we are playing with. And actually we extended the work that was done in the context of flood event to heat waves. So when you look at the bottom right, you have the minimum temperature time series. The minimum is usually the temperature you have during the night. And that was in Paris over, I don't remember how many years, but let's say more than a decade, because we have more than 10 lines. And the red one is 2003, right? So we have a very specific year in red, which was the big heat wave that happened in Paris in 2003. So this heat wave killed a lot of people in France, and it was not exceptional because of its intensity. It was not extremely hot. It was just very hot for a very long period of time. What you can see is for a few days, the temperature during the night was more than 10 degrees, 20 degrees, which is kind of hot. So this is something that has been observed in many countries. When you have a lot of people dying from heat waves, it's usually because the body cannot cool down during the night. So it's this kind of process we want this kind of property we want to observe in time series. And this idea of having some persistence is exactly what Hurst was calling a long memory, right? So it was this idea of auto-persistence in the time series. And in the paper I mentioned earlier, the idea was to present some papers and to discuss the difference between having long memory and having independence with heavy tails. So it was more a trade-off between heavy tails and having huge extremes and having persistence. And the two of them actually don't have the same kind of return period, right? So it was more or less what I was working on, but all of them are statistical and econometric models. The work that I've been working, the topics I've been working on more recently is slightly different. So just a little bit before the pandemic, I started working again on natural catastrophes, but I had a different angle. So instead of working on econometric models, we wanted to understand the fairness of models and see if it was possible to make some prediction, or at least short-term prediction, in the context of natural catastrophes. In this first paper, so we've been working on that with Laurence Barry from the Ppri, and Molly James. So Molly was a student at Oriab at that time, and now she's working at the regulation authorities in France. We wanted to get a better understanding of the natural catastrophe mechanism that exists in France and its fairness, right? So the idea of fairness is something extremely important in insurance. So this idea of actual fairness means that the premium should reflect the risks. So the more risks you have, the higher the premium should be. So it's what actuaries are using on a daily basis, which is try to find a premium which represents the risk. So you're going to use some features, some covariates to assess the risk of someone and then set the level of the premium, right? So it's this idea of actual pricing that we have in general insurance. The thing is, it's not what we use in this natural catastrophe mechanism we have in France. So if I get back to what is happening in France, so in 1946, so it was mentioned in the Constitution. So the Constitution is what's on top of everything, right? So it clearly says that there should be some solidarity and equality of all French people before the burdens resulting from natural disasters, right? So it's what mentioned here. So it says that there should be some solidarity and equality. So it's not about fairness, it's really about equality, right? So there should be equality. And a few years after, in 1982, a law created the Catnap System, right? So this idea of having a mechanism to deal with natural catastrophes. So it was designed in this idea of having this solidarity between everyone by pulling all the risks, the natural catastrophic risks together, right? So it was including flood events, drought, earthquakes, avalanches, but big storms like winter storms in metropolitan France were excluded, right? So the big typhoons or hurricanes in French overseas territories are covered, but not big winter storms that occur in France. But flood and droughts are included in this mechanism. So just to get back on this mechanism, so I'm going to make it as simple as possible. So when you look at the bottom part, right? So when you look at this part, you get the English version on the left and the French version on the right. So this is the classical insurance mechanism. In insurance, so you got a claim, so a disaster will occur, then the insured will ask for some indemnity to the insurance company. So there is an assessment of the size of the claim, and then the insurer is going to pay back, and possibly there will be some reinsurance. And since we deal with large claims, of course, there will be reinsurance involved. So that's the classical mechanism of claims management in general. In the context of natural catastrophes, it's more complicated because there is a layer between the occurrence of an event and the insurance company. So this is what we have here. So it's this big three-step component. The first one is that the mayor will be involved, right? So if you live in a town or a city, and if there's a big flood, then the mayor has to do something, right? So he has to say that there was a big event and ask for the what is called a préfet. So préfet is the local state representative, and the idea is to ask for a recognition of an exceptional disaster to the préfet. And then this request is transmitted to some inter-ministerial commission, which is going to recognize or not the disaster, right? So we have this very complex scheme. So first of all, it will be compulsory, right? So each time you have a household policy insurance, there will be a portion which will be dedicated to the coverage of those natural catastrophes. And the mechanism will always be the same. If you are hit by a drought, by a flood event, by an avalanche, it's not on your own that you're going to ask your insurance company. You have to go through this process. And first, you need a lot of people in the town to experience a loss. Then the mayor will ask for basically the state and the government to intervene. And if the government says, yes, there was an avalanche or there was a flood, then the insurance company has to pay back, right? So this intermediary level has a very strong impact. And because of this layer, which makes the insurance compulsory, then which is going to oblige actually the insurance company to pay something or not, right? So this commission is going to say if there was a disaster or not. Then we need to be a bit more specific about how this insurance will work. And more specifically, the level of premium is actually not exactly set by insurance company. It will be set by this commission, right? So every year, the level of the proportion of premium which is dedicated to the coverage of natural catastrophes is fixed, right? So it should be a percentage of the premium, of the household premium. So it's not risk related, right? So it's more or less based on the household insurance premium, which can be related to burglaries or to fire. So you have a fixed premium, more or less 6% of the premium, which will be dedicated to the coverage of natural catastrophes, whatever the risk you have. And it can be seen as fair because it says in the Constitution that it has to be based on the principle of solidarity. So you need this solidarity. So having a fixed and a fixed, so it's not exactly a fixed premium. It's a fixed percentage of the premium which is dedicated to the coverage of natural catastrophes, makes it kind of fair. but actually it's not related to the risks. And if the risk is not related to the risk, then we have some issues, because if the premium is not a function of the underlying risks, then you have some issues with prevention, for instance, right? So if people don't pay the exact, not necessarily the exact premium, but the fair actual premium, then there will be it will be difficult to ask them to do some sort of prevention. So we've been working on this first of all on flood risks, and then in the second work on drought. And we wanted to understand exactly what's happening, because we have now 40 years of experience of this mechanism, and we want to understand exactly what's going on. So is it okay to ask people living in risky areas to pay a premium which actually does not reflect the risks where they live in? So when we started discussing with the Caisse Centrale de Réassurance, so the Caisse Centrale de Réassurance, I didn't mention that, but it's the government, which is here, the reinsurer, which is here, but actually it's more than a reinsurance company. It's a reinsurance company dedicated to these risks that is backed with the government, which is government as a last resource insurance company. So CCR cannot bankrupt it. There will be the state is going to pay for it. So we have this Caisse Centrale de Réassurance. So we get the data for flood event from them. And when we start discussing with them, they told us that actually this mechanism was fair because actually poor people were living in risky areas. So there was some sort of amenity going through this Catnap mechanism. But we wanted to understand if it was okay and if it was possible to look at more specifically at the risks in those areas, because there are some risk maps, right, which were designed built by civil engineers. So those are official maps that you can find for almost all risky areas in France. So the first one I'm going to present is what is called Ppri. So I is for inundation, and it's mainly about overflow risks. So it's the first kind of risk that was considered in these prevention plans, right? So those are maps you can find where we have different cities, and we have some areas that are defined as officially risky, right? So this is what we have in the context of overflow. And this one is about coastal risks. So it's another one. So the first one was related to the fact that there was a river. So there should be a river near those areas. So it's possible, exactly as I was showing you before, that the level of the river goes extremely high, and then there will be water everywhere in the streets. And the second one is more related to areas nearby the ocean or the sea. So in that case, you can get big waves, and so not specifically tsunamis, but something like that. So you have a big heat wave, a big wave, and actually it's going to go inland, right? So it's another kind of risk. It's called PPRL. And in that case, for instance, we can see that we have a risky area and it's nearby the sea, right? So it's a different one. So we've been able to get information about those well-known areas. More specifically, it's possible to get the shape files, meaning we can get the polygons of those areas, and it's possible to understand exactly who's living there. We've been able to do that because there is a data set that was released recently, which is the Vente de Biens Fonciers, which is the list of all the houses, buildings, apartments that were sold and bought actually during a 5-year window. Right, so we can get all the prices of houses in those areas, right? So we got here 2 cities, 2 towns, Saint-Raphaël and Fréjus, and we can see that actually some houses are in risky areas. So we got in blue the risky area, right? So it's because there are some big rivers, and actually we can see that in those areas there are houses that were sold. So it's possible to look at the prices, all transactions, and see the prices in those areas. right? So here is another map, so we can get, so here it's not cities, it's more département, which is a regional level, right? So we have here Loire-Atlantique and Vendée on the left. So we can see that in some areas, it can be very risky, and there are a lot of houses there. So we wanted to understand and to answer a very simple question, which is more or less who's living in those areas. Because if you assume that the price of the household insurance is related to the value of the house, then we have more or less an assessment of the level of the risks by, or the premium actually paid by looking at the price of houses in those areas. So this is what we were looking at. So when you look at this graph, so first we have the coastal risk. So when you look at the coastal risks in those two areas, you have risky, non-risky. So you have the two regions on top and below. Then for each region, you have the difference between the risky area and the non-risky area. So meaning the one which is in the Ppri L, right? So L is for littoral, which means coastal risk. And what we can observe is actually in areas that are risky, except for this one, but actually it's related to only less than 40 houses sold. If we look at the other ones, it looks like houses in those areas are much more expensive than those in non-risky areas. So it looks like when you look at coastal risks, houses and apartments in those risky areas are more expensive. So possibly because you enjoy a nice view, you have a view on the ocean, and it's expensive. So in that case, we don't have poor people living in these areas, but actually rich people, right? So when you look at the overflow risks, so I got here 3 departments, we can observe that actually people living in risky areas have houses that are actually cheaper than in the non-risky area, right? So we can also go further on that one. We got a plus 5%, but again, it's in a very small proportion, right? But in most of the cases, you got the t-test, right? So we can compare the prices in the two areas. Almost everywhere, the statistics say that you have a significant difference between risky and non-risky areas. In the context of coastal risks, it's more expensive. In the context of overflow, it's less expensive. So obviously we have a problem. We have a problem because in some areas, yes, there is some sort of amenity because having a fixed price for the premium make it affordable for people living in those risky areas, but it's not fair because actually it's also working in the context of coastal risks, which is a risk where actually rich people enjoy the national solidarity. So there is some issue with this mechanism, and we were wondering if it was possible to get a better understanding of what's going on in terms of inequalities and stuff like that. So can we propose a better system for the Catnap mechanism? So we wanted to look at a very simple model where we have two areas, right? So instead of having a fixed percentage of the premium in France, then we were wondering if it was not possible actually to get a non-risky zone, like the one in green on the map, and the one in red, which would be the risky one. So the idea is just to sort all the towns, all the cities in France experiencing some risks, and then to see if we have different premiums and try to find an optimal level. So how we define those areas. So again, we sort all the risks per city, and then we're going to cut. So we're going to say, okay, the top. So we keep 10% of the portfolio in the risky area, 90% in the non-risky area, and we try to see exactly what will be the level of the premium. So this is the level of alpha. So alpha is the share of the non-risky area. So obviously in France, the risky area is much smaller. So we assume that the part of non-risky area, the green one should be quite large, right? So if we have something like 90%, we get something like that, right? So we have the percentage of the premium on the left and the premium in euros on the right. So for instance, with a 90% cutoff meaning that we have 90% of the people in France living in the green area and only 10% living in the red risky area. In the one with low risks, the premium should be 3.5 euros. On average, it was more or less, if there's only one region, it should be about 12 euros. So if instead of having 12 euros for everyone, the non-risky will pay much less, which is 3.5. And then the risky area, it would be much more. It would be like 88.5 euros, right? So we don't want to find an optimal alpha. I'm going to briefly discuss the fact that it's very difficult to find an optimal value for that one. But it's just to say that actually, if everyone is going to pay 12 euros, then obviously there's no incentive for prevention, right? So it's just to say that people living in risky areas should be asked to pay a little bit more than those living in non-risky areas, because there might be some fairness issues actually, because the risk is so unfairly distributed across France. There are clearly areas in which it's almost impossible to get a flood event in France. So instead of having everyone at the same rate, we wanted to know exactly what was going on if we had two different levels. The issues and why it's difficult to get an optimal value for this alpha is what we can observe, which is the fact that the two curves are increasing. So both of them are increasing in alpha. So if the idea is to say, okay, we want the premium to be as small as possible, then we have to lower alpha. But it's absurd because it's related to what is called the Will-Rogers phenomena. The Will-Rogers phenomena is something, so I just mentioned what you can find on Wikipedia. It's what happens when you have two populations. So in the context of I'm going to read what's written, which is when the Okies left Oklahoma and moved to California, they raised the average intelligence level in both states. And this is what happens actually when you got two sets of observations. So if you have two groups, right? So if you have group one and you have group two, then if you move that one to this one, so if the lowest from the large group goes to the other group, then we're going to increase the average in the two groups. Okay, that's more or less what we're doing here. When we would try to increase alpha, so what it means is basically that actually we try to get a risky area and put it in the non-risky area. So in that case, obviously we're going to increase the risk in the two, because when you take the smallest one from the most risky area, then it's going to the group of non-risky. So it's going to increase the risk in the non-risky area. So the premium will increase in that group. But also because we remove this one, which was the smallest one in this big risk area, then it will be even bigger for that one. Right? So it's very, very difficult to assess something. It's just the idea that actually when you do so, yes, the premium is going to increase in the two groups. The thing is there are less and less people in the second one. So for instance, if you compare 80 and 90%, right? So if we compare those two, so of course there will be only 20 here. There will be 20% of the people paying that price, which is like 25 euros, while in that one, so we got 10% paying a premium, which is more or less like 90. So the premium has increased, but the proportion of people paying such an amount of money is much smaller, right? So it's just half because we moved from 20 to 10%. Okay, so it's an issue that we have, which makes it very, very difficult because there's no way to set an optimal level for alpha. It has to be a political decision, right? So in our paper, we're just looking at different scenarios and try to see what's going on. We wanted also to cap it. Like, what if we cap the premium like at 100 euros? Okay, so in that case, well, it's going to be smaller in the non-risk area than what it is currently, which is 12 euros, but it's going to be much closer to this cap, right? So it's what we have in this context of flood risks. And so we discuss in the paper this question of the trade-off between risk and inequalities and welfare. I can just mention a little something, which is the fact that actually when we focus on natural catastrophes, there is a big issue, which is the fact that it's an individual risk in the sense that it's based on individual insurance policies, but it's a collective risk in the sense that actually on your own, you cannot do anything to do some prevention. Okay, so it's not because you try to understand, you start to understand that you're facing a big flood risk that actually you can do something for prevention. Prevention has to be collective, so it can be done on a city or town level. It can be done on a region. So instead of having like the country split it in two areas, like the risky red and the non-risky green, why not consider some sort of hierarchical model where the premium you're supposed to be, or the percentage you're supposed to pay, the percentage of the premium which is dedicated to natural catastrophic event actually will be based on the city, but also the region. So we're going to split the risk. So it's more a credibility-based model where we focus on the city, then on the region and the country. So we try to propose different things just to say that having a 6% flat premium everywhere is obviously unfair. And we wanted to discuss different scenarios, one with a split between two regions and another one which was a hierarchical model. So that's more or less what we got in this first paper. And then we started working on something different. So it was still with Molly. So Molly was still by that time a student in France. And it was done with Hani Ali. So he was working with Ppri, and the idea was not to use only the data from the Caisse Centrale de Réassurance, but also to use historical data from 3 big insurance companies. So we got more data, and we wanted to say something about drought events, especially see if it was possible to do some sort of prediction. Could it be possible to predict the cost of drought events in France? Because drought is related to subsidence in France. So it's a very specific risk, which is defined as follows. So it's this idea of shrinkage and swelling of clay soil. So it's related mainly to 2 components. The first one is what is called a geotechnical factor, based on the fact that actually it should be in cities or areas where you have a strong concentration of clay, right? So it's something that is necessary to have a subsidence claim. The other one is based on meteorological factors, right? So you need to have a very drought summer, and it's based on some idea of having an index with a lower than an event which is lower than the 25-year return period. So it should be sufficiently rare in this area. So it should be rare and dry to be eligible and to get the city recognized as hit by a natural catastrophe. Right, so we wanted to look at this kind of risk in France, which is extremely specific again, and it's I think France has a unique coverage of the drought risk around the world. So this is what we have in the data, right? So we have more or less 30 years of data. We have here the number of cities hit by towns, villages, hit by heat wave and drought event. And this is when we look at the spatial distribution of those events. So obviously, again, some areas are at risk and some areas are not at risk. Okay, so obviously you will never get any subsidence risk in the Alps. In Brittany, it's extremely rare. So in other areas, it's much more common. But so again, the risk is not distributed everywhere in France. And we wanted to do some predictions based on some geophysics and meteorological data. Okay, so we've been looking at different kind of data. So for instance, every year we can get some indices related to precipitation, related to soil temperature, related to humidity. Okay, so we can get different indices for all areas in France on a very small grid. The question was, knowing those quantities, could it be possible to predict first if there will be a drought or a subsidence event, and then what would be the cost, right? So we've been using data from insurance company to get the cost, but also the official Caisse Centrale de Réassurance data. So we know exactly who would claim the loss, who actually was recognized as a hit by a drought event, and then the amount of money. Okay, so we've been trying different kinds of model on that one. So for instance, here, so the idea is maybe I should just mention that here because it's important. If we want to get the prediction at some point, say 2010, then we're going to use all the past data we have. Okay, so we're going to use past data until 2009, and then we're going to use geophysics and meteorological data for 2010 and try to make a prediction, right? So we try to predict something about the claims frequency. So this one is on the frequency. So you can get different models. So very classical one is to get a Poisson model, but Poisson was not performing very well. So we tried different things, especially zero inflated. Zero inflated was interesting because in zero inflated model, you assume that you got much more zeros than what you can expect with the Poisson model. And actually it kind of makes sense in the context of this Catnap mechanism, because first you need a recognition of the event by the government. So if the government says no, you don't have any event, then you will get an inflation of zeros, right? So having this inflation of zero make it quite good. Having a negative binomial was a way to deal with the variability we had, but obviously in some years it was clearly overestimating the number of events. But actually the zero inflated is working quite well because when you look at the gray curve is the exact observed number of claims. And you can see that actually we've been able to predict the number of claims very precisely. So that we had some problem in 2015, but recently it was quite good actually. Okay, so it looks like those models are performing quite well in the context of predicting the number of the frequency of drought events. Here is another kind of model. So it's not using GLMs, but it was more using random forest. Okay, so random forest is possible. We can play a little bit with the loss function, and actually it's possible to get a random forest model for the frequency based on a zero inflated loss function. And again, it's not that bad. I mean, this is 2018, and we can see that actually the Poisson random forest and the zero inflated negative binomial actually is working quite well. The standard random forest is not working very well. We can see that there are some clear overestimation of the number of claims, right? But it's when we change the loss function in the random forest, it looks like we are able to get some good predictions actually, and those are predictions in the sense of forecast, right? So it's really based on the fact that if you want to predict what happens at time t, you just use past data, right? So we do it properly in this one. So just to show you not only what the prediction, but also the location. So here is what we predict. So here we got two models. So we focus on 2017. So we got the random forest Poisson on the left, and the simple GLM with zero inflated, which is the second one. Then we got the observed one. So we can see that we got big differences. For instance, this is where we predicted to get a lot of claims, but there was nothing. But actually, when you look at what happens when you look at the CCR data, then actually those cities actually, or those towns actually ask for a recognition by the CCR, but they didn't get it. Okay, so there was a drought event, but actually it was not officially recognized because it's in the gray area and it's not the green one. So we can see that our model is quite good to predict our claims, but actually it's not very good to assess whether it will be recognized by the government actually. Okay, so it looks like we at least we understand a little bit what's going on. This is 2018, which was a big one, but actually we can see that we're not that bad on that one because we clearly observe those which were predicted, and we also predict a lot of claims in these areas. So obviously we're not that bad on that one. And this is, sorry, and if you look at the paper, we will get much more. And then we can move from the frequency to the cost, right? So we want to have costs and destruction rates, right? So we have those data because of release rate, and we got the portfolio of 3 big insurance companies. So it's possible to look at different cities and see exactly the average cost for each drought event in those areas, right? So it's you can look it at the town level on the left or the département level on the right. So it looks like in some areas, claims can be extremely risky, while in other areas, it's obviously less risky. So it's possible to predict something. So just to mention, we can create a map. So sorry, I forgot to finalize the table on the left. Okay, so we can derive 3 different areas. Okay, the first one is where we have like 40% of the portfolio, one which is more or less the regions where we have no risks. Okay, so we do observe that actually this is what we have in Brittany. Okay, then you have zone 1 where you can get some losses, but it's quite rare, and you got 50% of the contract. And then you have zone 2, which is the area where you have much more claims, quite expensive and much more frequent. Okay, so we have 3 different areas. So here it's slightly more complex than the 2 we had in the context of flood, but it makes sense to have those areas. Okay, so we can look at those prediction of what will happen in the different areas. So this is what we have in the context of intensity of drought event for 2017. So we can see that what we got in terms of prediction is very close to what was observed in terms of Catnap predictions. Okay, so that's what we did observe, and this is what we get. So I'm going to go a bit fast, but there's still one thing we wanted to work on, and we're not very satisfied with that, which is the problem of how to take into account climate change. Because we can read here and there that actually there will be more drought events in the future, but it's still quite difficult to see. So drought events is what you have in this area, where you have a small precipitation, so not a lot of rain, and extremely hot. Okay, so it's dry and hot. Okay, so clearly this is where we are now more frequently, right? So you have 2020, 2019, 2018, 2016. So clearly it looks like we are more and more in this area, but still it's possible, like some years are just very normal one, I would say. Okay, so it's still very difficult to predict something without those information on precipitation and temperature that we use actually to make predictions about the cost, just because at time t-1, it's very difficult to say what will happen at times t in terms of temperature and precipitation. So we still have some issues we wanted to deal with in this paper, but it's not possible so far. So it looks like we can get a good model, but assuming that we know exactly what's going on in terms of precipitation for a given year. So it's possible to predict once you have observed the temperature and the precipitation. So this is what we had in terms of models for flood and drought events. I'm just going to focus now on 2 recent works related to this context of natural catastrophes. The first one is related to wildfire in Quebec, in Canada. So it's some work I'm doing in the context of the Joint Research Initiative. We supervise with Yacine Bouroubi, with Professor at Sherbrooke, a postdoc fellow, and we can get some data. So the good thing in Quebec is we have a very good surveillance website where we can get data from all the past wildfires. So those are all the past wildfires that were observed over the past years. So we try to get a better understanding of what's going on. So we were expecting to get something this fall, but it's clearly more complex than what we were expecting. The main reason is that actually So we do observe some, so here we focus in Abitibi, which is a small region in Quebec. So we have all those black points, which are established wildfires over the past 10 years. But so we got ones in the data set. So we want to understand why we got a fire and why not in some areas with given information, we don't have a wildfire. So we need to get zeros. The thing is in this kind of data set, we have only ones. So obviously we can get zeros, which is each point in space and time, which is not in the database, is a point where we don't have any fire. So basically we can get billions of zeros. So we got like 1,000 fires and billions of non-fires. So if we do that, we get something which is extremely imbalanced, right? So we need to select or create a database with 0 and 1s. So this is more or less what we're using. So we have red points, which are points that were, so we try to do different things. So we try to get points nearby a location where we got a fire like a few weeks or after or before. We try to move around just a year before and so on. So we try to get zeros and try to get some predictions and try to see more specifically the impact of 3 kinds of variables. The first one is about meteorological data, about how hot it was, about humidity. The second one is about vegetation. So we use satellite pictures to assess if the trees are very dry or not. Okay, so we can check the humidity of in trees and stuff like that. We can observe also some lakes, some areas with a lot of humidity, so it's possible to say something on the map. And the third one is about human activity. Okay, so we also take into account how far do we have a road, do we have houses. We also try to take into account electric wires, right? So we try to understand exactly how important are those 3 sets of features, how possible it is to predict a wildfire given those 3 covariates and see something. So we try to relate that to temperature and climate, to vegetation and human activity. So it's first, it's a very interesting question from a methodological perspective, because we have to understand exactly how we create those zeros. And I know that some colleagues in France are working on similar stuff on thunder and lightnings, right? So it's a classical issue in the context of spatial temporal risks, and it's something which is we will finalize very, very soon. The second one is very, very different. So it's not based on data. It's more it's based on a paper that I published like in 2015 on government intervention. So my question was, in this initial paper in the Journal of Political Economy, Public Economics, sorry, what happens when you have 2 regions where risks are correlated and you don't oblige them to purchase reinsurance or insurance against natural catastrophes? So there will be correlation because of the spatial correlation of natural catastrophes. But we were wondering what's happening if you got 2 regions. One of them is going to purchase insurance and the other one is not. And in that case, what we prove is just using this problem of solvency, that actually some people, well, in some cases, you will not have any market, because if the area is too small, then people will not buy insurance. But if you have a bigger one, then it's very likely that you will have insurance, which is more or less the idea that you have in the French mechanism. So we had this paper where we try to understand how government should intervene in the context of natural catastrophes. And we're currently working on a model to understand how government should learn and try to do something to help people to get insurance coverage. So it's a paper on what we call government intervention in the context of reinforcement learning. So reinforcement learning is the idea that an agent can take a decision. So he's going to make an action. So for instance, we have a government which is going to say, okay, I'm going to make insurance compulsory. Okay? I'm going to ask an insurance company to get more capital. I'm going to do some prevention. I'm going to inform people about the underlying risks, because we assume that we have some bias in the population. So government can do something. And when it's doing something, then there will be a feedback. And then other players will change what they do. Okay, so if the government is going to, say, have a compulsory mechanism, then obviously the insurance company will have to adapt, and then insurers also. So we have three different kinds of agents. We got the insured, we got the insurance company, and then we got the government. And we try to make them interact all together. Then the only one which is going to take actions and get feedbacks is the government. Okay, so at each step is going to take an action, like possibly because a big flood occurred. So basically there was no flood insurance in the market, and then there was a big flood, and then everyone lost something. So after this big storm, they're going to do something about that. So it can be create a scheme, it can be I don't know, play on the taxes or whatever. So we have different kind of actions that the government can take, and we try to understand how it's going to help the insurance market to live and what's going on. Okay, so this is what we study in this article. So that's more or less, we have a big neural network model. This is all the kind of actions that the government can take. And then we try to look at the kind of feedback you will get. So by taking an action, actually, there will be something. So there can be some bankruptcy of insurance companies. Then they can get more coverage and stuff like that. And then it's going to adapt. Okay, so it's a joint work we hope to finalize very soon, but it's more a very high level where we try to understand exactly how government should intervene, which is actually, this is why I wanted to mention that here, which is actually very related to what I was talking about before, which is try to understand the mechanism that you can observe in France, try to see if it's fair or not, how to change it and stuff like that. So I think all those works are connected, and this is what I was willing to show you today. Okay, so just to go further, so you can find all the work related to the Joint Research Initiative on the website dedicated to it. You can find all the papers on my website. I can just mention two other works which might not be directly related to those issues, but I recently published a paper, a report on insurance biases, discrimination, and fairness for the Institut Le Bachelier. So it's, I think, related to this question of fairness of the Catnap mechanism in France, but we go much further because we discuss gender and racial discrimination in insurance. So it's something slightly different in this report. And I can also mention some work I've been doing, which is maybe some of you have been playing on that one, which was the insurance pricing game we had last year with AI Crowd. So we got 2,000 players, 10,000 models submitted. So it was in the context of motor insurance, but it's still about this question of insurance equilibrium in the context of having multiple insurance companies. So it's more or less related to this question of reinforcement learning that I was talking about before. In the work I was talking about before, reinforcement learning was studied in the context of government taking actions. Here in this pricing game, we want to address the problem of reinforcement learning in the context of insurance company, because when an insurance company set a level of premiums, then he's going to learn not only from his portfolio, but also from the market. So if you see that the market is performing well and not you, then you have to adjust and stuff like that. So it's more or less what we have in this pricing game. Okay, so I'm going to end here. Afterwards, you will get references about all the papers that were mentioned in this talk, and thanks a lot for your time.